Hi, my name is Amy Sullivan, and I'm the current president of AAAR. It's my pleasure to welcome you to the 33rd of our monthly AS&T lecture series. This is a new initiative for AAAR being supported by the Freelander Memorial Fund. So each month, the editors of AS&T select a high impact paper to be presented by its authors. We also hope with these lectures that we're able to highlight the amazing research happening in our community, to give us all an opportunity to come together outside the annual conference, and also to tie our journal AS&T to other activities in AAAR. So these lectures are being recorded, and you will be able to access them after on AAAR's YouTube channel, which you can access from the AAAR website under the AAAR Events tab. In addition, each of these lectures is being hosted by one of our student chapters. With that, I want to thank all of you for joining us and everyone who's helped to make these happen. And with that, I'll turn it over to our student chapter from Washington University in St. Louis. Thanks.
Yeah, thank Amy for the brief introduction. So, hello everyone, and welcome to the AAAR Spring 2025 seminar series today, hosted by the Washington University in St. Louis chapter. So, my name is Zhao Hengqian. I'm currently the president of the AAAR student chapter here, and today it's our pleasure to invite Dr. Prakash Gautam from the Desert Research Institute, which is located in Nevada and is part of the higher education system of University of Nevada. And just wanted to briefly and quickly introduce the background of Dr. Gautam. So people might already seen the introduction in the announcement email. Dr. Gautam is described as a postdoctoral researcher. However, I would like to announce an update. So actually, Prakash is formally starting from this month as a new position as a assistant research professor at DRI. So this is the latest update of his status. And actually, Prakash completed his PhD at Kansas State University, and he is engaged in research combining experimental and theoretical aspects of electromagnetic and light scattering, particularly in atmospheric, climate, and aerosol physics. His work involves designing and developing a multi-angle light scattering setup for real-time in situ characterization of particle properties of aerosol particles, such as mineral dust, ice crystals, pollen, and bioaerosols. These optical properties include phase function, extinction, such as scattering and absorption, asymmetry parameter, single scattering albedo, lidar ratio, linear depolarization ratio, and other scattering matrix elements. His recent research has been particularly focused on the development of several key instruments and concepts, so including a cost-effective sensor for monitoring ambient particulate matter using near-forward scattering, and also a polar nephelometer capable of measuring light scattering from an extreme forward scattering angle to near exact backscattering angle, including several others. So considering the time, without further ado, I would like to invite you to join me and welcome Dr. Prakash Gautam.
Thank you.
Yeah, Prakash, the floor is yours.
Okay, thank you, Amy and Zhao, for these nice introductions. So here I'm going to give some resource related to the light scattering from spherical and irregular aerosol particles over a wide angular range. So what are the aerosol particles? Aerosol particles are solid or liquid particles suspended in the air that sizes from nanometer to micrometer range. They are produced from natural and human-made processes and have a significant impact on air quality, human health, climate, and weather patterns. Here you can see some of the examples, that is industrial activities, forest fire, volcanic eruptions, bioaerosols like pollens, and desert dust and automobiles. These are some examples of the aerosol generator in the atmosphere. And then light scattering is one of the technique that can reveal the secrets of those particles without changing their morphology, size, and other physical and chemical properties. What is the light scattering? Light scattering theories can be classified into three different, like Rayleigh scattering, Rayleigh-Divine scattering, and Mie scattering. Rayleigh scattering can apply to particles of any shape, but the size of the particles should be smaller than the wavelength of light used to investigate those particles. And that is characterized by the internal coupling parameters, that is rho prime equals to twice kr m square minus 1 divided by m square plus 2 equals square. And this is internal coupling parameter, which is similar to the phase shift parameters, that is Van der Host, but this internal coupling parameters is deployed by our group at k state, and that involves both size parameter of the particles and Lorentz factor. And Rayleigh-Divine scattering. Rayleigh-Divine scattering applies to any shape, just like Rayleigh scattering, but this is for any particle size. And that is also the internal coupling parameters should be less than 1. And then Mie scattering. Mie scattering can apply to spherical shapes of any size, any refractive index, and any rho prime. The question is how we can get how can we explain the light scattering from irregularly shaped complex particles with diverse microphysical properties, shape, size, and complex refractive index coherently and comprehensively. It is still a very challenging. There is no any theory that can explain the scattering from irregularly particle shaped of diverse microphysical properties. And here for the wide angle light scattering data, we advocate to plotting the scatter light into two analysis method, that is called Q space and theta space. In theta space, you plotted the scatter intensity versus scattering angle. And what about Q space analysis? Q space analysis is the analysis developed by Chris Sorensen at K State, and that is here we can explain this. Any particles can be characterized by infinitesimal many point scatters like that. And let's take one point scatters and incident by the incident light of a vector k incident that gets scattered at an angle theta, and characterized by the scattering wave vector k scatter and falls on the detector. When the detector is very far from these particles, then the electric field that is detected by the detector is sum of e power I q dot r, all the phases of the particles. And if the scattering is elastic, and then you have a incident wave vector is equal to the scatter wave vector, and which is 2 pi by lambda. Then scattering wave vector is the differences between the incident wave vector and scatter wave vector. And with the simple mathematics, you will get Q equals to 4 pi lambda sine theta by 2. Now Q has a dimension of inverse length. Now we advocate to plotting the scatter intensity versus Q or QR. Here R is the sphere radius on a log-log scale. Phase function. In today's talk, I will focus on the phase functions of spherical and irregular particles. What is phase function? Phase function tells us how the scattered light is distributed over different angles after interaction with particles such as dust or molecules in the atmosphere. Here, I'm trying to show you that how the incorporating both analysis method theta space and Q space helps to get a coherent and comprehensive explanation of scattering, wide angle light scattering. Here, the same data is plotted in theta space and Q space. Here, this is called the forward scattering regimes, and this is side scattering, and here it's called the back scattering regime. Here in theta space, you don't see anything information from this plot until here, but it shows some functionality towards the backscattering. The same data is plotted here in Q space, which is normalized at smallest angle 0.32 degree that our experimental setup can measure. Here you can see the constant forward scattering lobe followed by Guinier regimes here and power law and enhancement in the backscattering. Here from Q space you can see the forward scattering lobe and Guinier regime. From Guinier regime, I will explain in the later slides how is the Guinier analysis helpful to estimate the particle size of the scatterers. And here, the disadvantage of Q space is towards the backscattering regimes, where all the data are compressed by Q space analysis on instead of theta space here. So in the left in theta space, you see detail in back directions. In Q space, you have seen forward, lobe, and Guinier regimes, and power law regimes. So to get the comprehensive explanation of wide-angle light scattering data, you need to explain both, you need to plot both same data in both analysis method, theta space and Q space. Application of Q and theta space analysis method for spherical and irregular particles. Here I am showing a demonstration of Q and theta space method to interpret light scattering from spherical particles. They are the forward normalized at 0 degree. The same data is plotted in theta space and in Q space. In theta space, you can see here the scattering pattern looks very bumps and wiggles, no any coherent pattern here. But when the same data is plotted in the Q space, you can see constant forward scattering lobe followed by Guinier regimes and with the crossover of slope -2 and -4 and followed by an enhancement in the backscattering. Here, the particle size ranges from 0.5 micron to 16 microns. Now you can see how messy the scattering pattern when you plot the intensity in theta space compared to Q space. What about the irregular particles? For irregular particles, this is a schematic diagram of in Q space. That is intensity versus Q in a log-log scale that gives forward lobe followed by Guinier regimes where QR is equivalent to 1 and followed by power law and enhancement in the backscattering, that is glory. And then this is the data that is published by Uli Hansen 2016. And these are the data generated at famous light scattering group at Spain, Granada, and Amsterdam light scattering group. Here you can see no constant forward scattering lobe and Guinier regimes because their setup is measuring the scatter light from 3 degree to greater than 3 degrees. So they are missing the forward scattering angular range that our setup is measuring. Because of their limitations in their experimental setup, they are not measuring the forward scatter light. So we are not seeing here forward lobe. For bigger size particles, you need a small angles. As much as small angles you get, you can get the light scattering in for particle size for the bigger particles. And then wide angle light scattering setup. This is the light scattering setup that is located at K State. And here in my work, I use the 532 nanometer laser. And here you can see the scattering volume at the near focal point of elliptical mirror that you can see these scattering volumes. And the two detectors are used, detector 1 and detector 2, to measure this scatter light from 0.32 to 178 degree. Now, currently at the Desert Research Institute, I am trying to develop similar setup, but with replacing this photodiode detector with a photomultiplier tube and with replacing 2 detector by 3 detectors so that you can get all these like 64 different angles, scatter intensity at 64 different angles from 0.3 degree to 178 degree. Now in the coming slides, you can see the light scattering results from irregular and spherical particles. Here, light scattering from spherical silicon dioxide and highly refractive molybdenum disulfide particles. Here you can see the comparison of experimentally observed light scattering data with me calculations for APS observed particle size distributions for silicon dioxide particles and molybdenum disulfide particles, and the size distributions measured by aerodynamic particles and intensity weighted distributions. For intensity weighted distributions, light scattering at the forward scattering regime, when the particles are of micron size, then intensity is proportional to diameter power 4, and that gives you intensity weighted distributions. Here, the interesting is you see the enhancement in the backscattering. In case for SiO2 particles, unlike molybdenum disulfide particles, you do not see any enhancement in the backscattering here. This is due to the fact that in spherical particles, in silicon dioxide particles, you have zero imaginary part. So there is no absorption. That means an enhancement in the backscattering occurs. But in case of MS2 particles, this is highly absorptive in nature. That has 1.16 imaginary part of the refractive index. That gives the kappa kr. Kappa is imaginary part and kr is the size parameter of the particles. And when kappa kr greater than 3, essentially you do not see any enhancement in the backscattering. This is kappa kr is called the relative skin depth parameter, that when if kappa kr is greater than 3, then you will saturate the effect of K. There is no any saturation. All the light that enters into the particles is absorbed by the particles. So in this case, there is no rainbow of glory. And here, the interesting point here is that how the intensity weighted distributions compared to the number weighted distribution measured by aerosol measuring instruments such as aerodynamic particle sizer. Here, for aerodynamic particle sizer, you have a number weighted distributions more at 1 micron. When you convert these number weighted distributions to intensity weighted distributions, that is converted by multiplying the size of the particles with diameter power 4. And you see here the peak is around 4 micron for intensity weighted distributions. Similarly, for MOS2 particles, the number weighted distributions peaks at 1 micron and intensity weighted distributions peaks at around 3 microns. See, light scattering favors the larger size of distributions. Here is again the advantage of Q space analysis is allow you to get the Guinier analysis based on the extreme forward scattering data. Here you can see we do the Guinier analysis with this equation. That is the equation developed for X-ray scattering, and here is the equation. IQ is the intensity at Q, and RG is the radius of gyrations, and we have these equations and plotted here. So what we observe from light scattering in for particle size for SiO2 is 4.8 micron, and for MOS2 is 3 micron. That is consistent with intensity weighted distribution size, 4.5 micron and 3 microns here for MOS2 case. For larger particles, few data points for Guinier analysis. That's why to get the light scattering for particle size, you have to measure very small, extremely small forward scattering angle range. Here, the important message is when you interpret the light scattering in for size from the aerosol measuring instrument like APS, then you have to careful on this intensity weighted distributions, because here if you have 100 number of particles with 1 microns and a few particles with 4 micron, these few particles contribute more to the light scattering compared to hundredth of small size particles. Now, light scattering from highly absorptive non-fractal hematite aggregate. Here, I experimented the scattering from hematite aggregate that has highly absorptive in nature. That is 0.5 is the imaginary part of the refractive index. So this is the images of hematite for scanning electron microscope, and this is optical microscope. Optical microscope shows that the particles are bimodal in size distributions, but scanning electron microscope shows that your particles are aggregated in nature. So we tested whether these aggregate are fractal or non-fractal. We did the ultra-small angle X-ray scattering. And what ultra-small angle X-ray scattering? For this, we get the power law -4 and -4. These regimes correspond to 10 power 4. That is equivalent to 1 microns. And this is equivalent to the like 100, 200 nanometers. That is what we observe for monomer range and aggregate range. This shows that the power law, that is polar regime of -4, indicate that our particles are not fractal, they are non-fractal. Here, the interesting results that we observe from our light scattering, small angle light scattering data shows a constant forward scattering lobe followed by slope of -0.5 and then -3 with enhancement in the backscattering. Our theoretical calculation shows that there is no enhancement in the backscattering. There should not be enhancement in the backscattering for solid spheres equivalent to the particle size that TEM, that our SEM shows. Here, another interesting fact interesting results is you have seen two Guinier regimes, first constant and one in first inflections and another inflections here. That corresponds to 0.3 microns and that corresponds to 10 microns. So this indicates that the particles should be bimodal size distribution that is consistent with these optical microscope pictures. If you compare this data to the Q space, to the theta space, you do not see any information with this plot here, unlike this. To interpret, to understand, like to verify our experimental data with the theoretical calculations, we performed T-matrix calculation by assuming, by simulating the hematite aggregate with variant Eden growth model to fit XU6 data. This is we modeled particles safe, just like the hematite particles. We took the number of monomers as 346 and did the calculations. In our calculations, we generated bimodal size distributions by incorporating 70% 1 micron and 10%, 30% 10 microns particles. And then we did this scattering calculations. You can see here is a single inflections for individual particles, 1 microns and 10 microns, but the sum of intensity gives you constant that is followed by slope -0.5 with -3 parallelisms, consistent with our experimental results. This again emphasizes that when we have a phase function measurement, it is better to plot in the Q space, not only in the theta space. Here in theta space, you will not draw any informations about the particle size and particle size distributions. And in the next slide, I will talk about this enhancement in the backscattering. Why we are seeing the enhancement in the backscattering, that the me calculation with the size that is equivalent to the hematite shown in TEM and optical microscope do not show enhancement in the backscattering. Here, you can see this calculated forward normalized scatter intensity for aggregate formed as a spherical volume with a diameter 2.4 micron and with the monomer diameter 200 nanometer, that is equivalent to the monomer size of the hematite aggregate seen in SEM. What we see here is we have performed the individual calculations of monomer. You have seen some enhancement in the backscattering. With solid sphere, you will not see an enhancement in the backscattering. For aggregate, you have seen an enhancement in the backscattering. That is calculated for refractive index 3 and 0.5. That is the refractive index of hematite particles. What happens when we have no imaginary part? Like I said earlier, there is no imaginary part, there is no absorption, essentially no absorption, and all you can see is an enhancement in the backscattering. Here for monomers, you have seen enhancement in the backscattering more than that you see here, because here is the 0.5, the refractive index that kills the enhancement in the backscattering. Here you can see greater enhancement in the backscattering because there is no imaginary part. And again, the solid sphere is not showing the enhancement in the backscattering. What happens here in this plot, we try to kill the enhancement in the backscattering from monomer by increasing the imaginary part. See, first 0.5 equivalent to hematite, no imaginary part, and then here highly imaginary part that is killing the enhancement from the monomer. Again, from the solid sphere, you do not see an enhancement in the backscattering, but you see, still you see an enhancement in the backscattering from aggregate structures. That makes us the conclusion that the enhancement in the backscattering from hematite aggregate is due to the internal multiple scattering between the monomers within the aggregate. Now, light scattering from highly absorptive fractal soot aggregate. What happens to the fractal soot aggregates? Fractal soot aggregates are like a self-similarity scale invariant, and their structure obeys the power law is given by these equations. And N is the number of monomers within the aggregate. Number of monomers within the aggregate, and K naught is prefactor that determines the shape of the fractals, and RG radius of gyration, that is overall size of the aggregate particles, A is monomer radius, that is around 20 nanometers, 30 nanometers, and del F is the fractal dimension that gives the overall morphology of the soot particles. Here I generated the soot particles by two methods. One is lab-made premix burner, another commercially available inverted soot generator from Argonaut. Here in lab-made premix burner, I use the ethylene and propane and oxygen as a precursor to generate soot particles. And the good thing is that we can incorporate this directly into the bottom of the scattering setup, so that you will scatter the soot within a few seconds, maybe 10 centimeter distance from the soot generators. So you see very ramified, not a compact soot aggregate, unlike this inverted soot generator. Here, I cannot use this soot generator directly within the setup. So I generate the soot particles like 2 meters away from the optical setup and takes the soot particles using the tubing, and then measure the scattering from the soot particles. Here, the TEM pictures of the soot particles generated from this instrument. And when you compare to the soot morphology here to here, it looks like a completely different in nature. This looks like a fractal dimension of 1.8, and this looks like a fractal dimension greater than 1.8. Is very compact and looks like a super aggregate soot. Here is the light scattering results. So this is the light scattering results of the soot generated by premix burner and corresponding TEM pictures. Here, again, the interesting results is we are getting the enhancement in the backscattering. The fractal dimension minus 1.8, that is consistent with the diffusion limited cluster aggregations. That is the soot, very nascent soot, but we see an enhancement in the backscattering. What is the results for the soot generator from argonate soot generator? Here you can see in the argonate soot generator, you change the fuel air to fuel ratio with different magnitude, and then measure the scattering properties. And here you can see the power law of -2, fractal dimension minus 2.4, 2.15, 1.95. It looks like a compact soot instead of the ramified nascent soot. Here is these are the data for 0.32 degree to 10 degree. Here, when you misses the power scattering, then you are missing this regime. That is, the interesting here is when you have a air to fuel 104, and then you have seen constant goes here, and first inflection and second inflection. That is similar to the what we observe in the hematite aggregate, maybe bimodal size distributions. The interesting fact here is, again, we see the enhancement in the backscattering. We did the similar calculation theoretically, just like in hematite particles. We still do not see why we are seeing the backscattering from soot aggregate. This is still needs to understand why we are seeing the enhancement in the backscattering. That theoretical calculation shows no enhancement. Light scattering from spherical water droplet. Here you can see the light scattering from the water droplet that is generated from TSI nebulizers. Here the comparison between the experimental results to the calculations. The best fit values are weighted mean radius are 1.2 microns and geometric width 1.45 and water refractive index 1.33. And then we have a very, the same data is plotted here in theta space and in Q space. In the forward scattering regimes, they are all overlapping. That is consistent what we observe, because in forward scattering regimes, there is no electromagnetic interaction. There is just diffractions, and forward scattering is fairly insensitive to particles morphology and particles shape and complex refractive index. Here you can see the backscattering, how chaotic looking backscattering. Here you can see what I do is I just change the weighted mean radius by 2.5%, like 1.25, 1.22, and 1.28, keeping the geometric width constant in all cases and refractive index constant. You see how messy towards the backscattering regimes. Here, in 2.5% change brings a factor of 3 towards 180 degree. Backscattering sensitivity to particle microphysical properties. Here I am only showing the backscattering regime, not the forward and side scattering, because backscattering is very sensitive to remote sensing lidar applications and remote sensing detections. So here what you can see is in A, you have changed the weighted mean by 2.5%, keeping particle size distribution constant and refractive index constant. Here, you have changed the size distributions by 2.5%, keeping weighted mean size same and refractive index same. Here, you are changing refractive index only, keeping weighted mean size and sigma same. See how the messy is in the backscatter regimes. Even with 2.5% change brings a lot change in the within the backscattering regimes. Another interesting here the calculation shows that the refractive index of water changes with temperature. See, I have changing here the refractive index by 0.01. That brings such a chaotic pattern towards the backscattering regime. What about backscattering sensitivity to the particle shape and aspect ratio? Here I am showing the demonstration of sensitivity of backscattering effect of shape is spheres versus spheroid. Here again I have changing the sphericity of the particles by 2.5% and the calculator for two polarized light, vertically polarized light and horizontally polarized light. The data are normalized at 178 degree. Then even 2.5% brings a lot change in these backscattering regimes. This is from 174 degree to 180 degrees. Here, 2.5% brings a order factor of 2 or factor of 3 changes in the backscattering regimes. That shows that how sensitive the particle shape when you analyze the backscattering data. And here, this is the data that is calculated from Mission Code 2005. And this is the calculation for prolate spheroids and changing the aspect ratio from 1.2 to 2.4. And for spheres, you have seen the bump at very near to 180 degrees. As you changes the aspect ratio, that is increases the aspect ratio, you are seeing the bump coming towards smaller scattering angle. So there might be some pattern that sphericity brings based on the experimental data, we can estimate the sphericity of the particles. This again looks chaotic. Even such a small small change in aspect ratio brings a lot change in the scattering pattern. So that shows that backscattering is strongly dependent on particle size, size distribution, shape, and complex refractive index, which is indicative of compositions. Thereby, interpretations of backscattering data requires accurate characterization of particle physical properties. And we have seen that many people are extrapolating the backscattering data from 172 to 173 to 180. That is erroneous. And here I'm showing that is it accurate and reliable when you extrapolate the backscattering data from 178, 179 to 180 degree, because it is very easier to measure the scattered light at 178 degree compared to 180 degree. Here you can see the backscattered light that is plotted versus phase angle 180 degree minus theta, and here is the data for up to 2.5 microns. This is for water droplet particles. This is for spherical particles. And here you can see that in the last 1 degree, you have seen plateau. It's constant, no functionality on the scattering patterns. That indicates that if you measure the scattered light at 179 degree, then you can accurately extrapolate the data towards 180 degree. This is for ensemble of particles. But when you work with these single particles, then there might be not the case. But for irregular particles, then irregular particles of any size, then you can extrapolate from 170 to 179 to 180 degree with a great accuracy. Here, wide angle light scattering from irregular aluminum oxide particles of different sizes. Here, I am showing you the comparison of the experimentally observed forward normalized light scattering data with me calculations for APS observed normal size distributions. Here, in the first row, you can see the light scattering data for 3 microns, more size distributions, and in the lower row, you can see scattering from particles with more size distribution, 9.3 microns. The interesting thing is in the side scattering regimes. In the forward scattering regimes, you have overlapped from experimental to me calculations. That is what we observed in spherical particles too. In case of forward scattering, you see the discrepancy between the me calculations and light scattering. Here, less compared to here. The thing is that what we observe is if you increase the particle size, then you can see the discrepancies increases between the me calculations and experimental results. So what happens to the backscattering? We plot this data to the backscattering data in terms of phase angle, 180 degree minus theta. And here what we can observe is the crossover. For small size particles, 3 microns, you have seen crossover at around 13 degree phase angle. When you have a bigger size, then it's coming towards near, is maybe 9 degrees, the crossover. So I'm not showing the other particle size distribution results in between these 3 and 9.3 microns. So there is some pattern on the crossover between the me calculations and light scattering results. So this is the indicative of there is some pattern to find the scattering from the irregular particles and predict the microphysical properties of the particles based on the experimental results. Key takeaways from the presentations. Although there is a comprehensive understanding and documentation on scattering by spherical particles, the scattering from irregular particles continue to pose significant challenges. A complete explanation of light scattering from any particles requires wide-angle data and analysis both theta space and Q space analysis method. Wide-angle data here, many people are saying in their literature, in their paper, they are wide angle, but they are missing the forward scattering angle. Some 10 degree to 170. This is not the wide angles for me, because you are missing the most important forward scattering regimes. For example, so when you have a particle size 10 microns, 50% of the light will fall within the first 1 or 2 degree. So it is very important to measure the extreme small forward scattering angles. Small angle light scattering data is key for determining particle size distribution in larger particles, while scattering in forward particle size are important for backscattering analysis. Careful interpretation is required when comparing light scattering in forward particle size distribution with those from commercially available aerosol measuring instrument, particularly for ensemble particle characterizations. To provide a coherent explanation of light scattering from irregular particles, extensive wide-angle data on aerosol particles and their interconnection with microphysical properties. You have got the light scattering results, and at the same time, you need to characterize the particle size, shape, compositions, refractive index, internal structure, and morphology that are necessary to get the coherent explanation of light scattering from irregular particles. References. So most of this work will be found in this textbook that is wrote by my supervisor Christopher M. Sorensen. So you can get all these kind of informations in this textbook. And my acknowledgement goes to Chris Sorensen, Hans Mosmuller, DRI, Matt Borg, KSU, Justin Morn, Pratt Community College, and Uli Hensons, Raya Ibini, American Ecotech, and Kansas State University and Desert Research Institute. So looking for a collaborations. If anyone experimentalist or theorist is interested in working light scattering from aerosol particles, including mineral dust particles collected from various dust internment areas around the globe that our lab in the DRI have access, and would like to use the wide angle light scattering setup and measure angular reserves data, please feel free to reach out to me. Thank you.
Well, thank you so much for the very informative and insightful presentation. So right now, the floor is open to the audience for questions. So if you have any questions or even like just comments or ideas to share, or like just Dr. Gautam just mentioned, if you are looking for collaborative opportunities, just feel free to unmute yourself and like throw them out.
Prakash, am I coming in?
Thank you. Hi.
Okay, good. Very beautiful talk. Here's a crazy idea for you. You have all of these patterns in Q-space analysis, and then you have data where you plot your intensity as a function of phase angle, alpha. Are there patterns in Q-space when you replace theta by alpha? Do you understand what I'm saying?
Oh, theta by alpha. Okay.
So like in the very beginning of your talk, you talk about the Guignay crossover and the power laws. What if we just try to rederive all of that? Instead of using theta, we use alpha. Do we find anything useful?
Yeah, so maybe in the same, that is not theoretically correct, but in Q space, just 4 pi by lambda sine theta by 2, if we replace theta by alpha, then I think we can get some pattern on the backscattering. I have not started doing this, but there might be.
Well, what I'm getting at is, Chris has shown a conceptual explanation for these patterns in terms of, little subvolumes and various length scales in a scattering system. So it may be that you can use that general idea and kind of invert it to be in the backward direction. But it's just a thought.
Yeah, that's what I'm thinking. Thank you so much. I will start working on this to find this, if there any pattern.
Okay, congratulations.
Thank you.
Well, thank Matt for the comments or suggestions. And any other questions? I see the advisor of our WashU student chapter of AAAR, Professor Rajan Chakrabarty, also an expert in aerosol optical properties. Would you like to comment on Prakash's research?
Yeah, Prakash, can you hear me?
Yes, I'm hearing you.
Yes, yes, a very good talk. Congratulations, first of all, on this extensive review and all the contributions you have done, following on the footsteps of Chris, and also for landing a faculty position at TRI. So it's always good to be connected to my past institution. I was very interested in your alumina particles. You show the results, uh, and you start from 3 micron all the way to 10 micron, correct?
Yes.
So this is more of a comment. So we are right now working on submicron or like less than 1 micrometer alumina particles.
Mhm.
The idea here is that these particles are prevalent in the stratosphere from a spacecraft re-entry. And so they're in the aerosol phase, but they are extremely small, much smaller than the size you probe.
Mhm.
And they can agglomerate. They are also non-spherical, and they can be in different phases. So that is one interest. Alumina is also a candidate, a highly probable candidate for stratospheric aerosol injection for geoengineering. But there is a lot of uncertainty with regard to the directionality of scattering, like how much, if you were to seed the stratosphere with these aerosols, or even the aerosols which are present, how much of backscattering, ideally you would want sunlight to be reflected back in the
Mhm.
visible. So I think what the work you are doing is really beneficial. My only two cents would be if you could perhaps probe particles less than in the smaller sizes.
Size
So that
range.
will have a direct application. Uh,
Mm.
and also maybe show some images. Maybe I have to read your ASNT paper, but show the images of the non-spherical particles, because alumina can have different polymorphs. It can have, alpha, gamma, and depending on that, the index of refraction will change.
Mhm.
Absorption will change because
Yes.
there are defects in most of these commercially manufactured alumina particles.
Mm.
So, what is the role of absorption if you introduce it? How would your Q space or your phase function
Mhm.
change?
Yeah. Yes.
And we can circle back after this offline in a different thread. I'm sure I am ready to send you some samples to
Yeah,
probe.
sure. I am here now more advanced light scattering setup than K-state. So maybe I am replacing in K-state. I work with the photodiode cathode ray, and they are less sensitive than PMT tube. So currently I am working with the PMT tube that can also possibly detect the single particles as well. So we can definitely work on it, and yeah. If you go to the like less than some micron, less than like around 300 nanometer, it is very difficult to measure from light scattering. It's late scatter light. So
Correct.
if you
Correct.
have a size around 1 micron, 500 nanometers on
Yes.
100 nanometers, then it is capable. Like our setup is capable to get the scattering, to measure the scattering from such particles.
Okay. Thank you.
Yeah,
Thank you.
please let me know whenever you wants to do a wide angle light scattering from any
Sure.
kind of particles.
Yeah. Thank you. And congratulations again.
Thank you.
Yeah, thank Professor Rajan Chakrabarty's comments and question. So is there any other questions from the audience? Please free to unmute yourself. If no one else, I actually have a question. So I think Prakash's this presentation, this is very insightful. Like this provides a very valuable information for people in the field of aerosol optical properties. But I have a question that is more related to like past field measurement data. Like for example, in the past when people didn't know this, like this properties are measured from like very wide angles. Like
Mhm.
if you want to compare the data with previous studies, especially field campaigns, not lab field data. Like they usually they only have like the bulk absorption data, and
Mhm.
then like how will you extend this finding from your wide angle uh, information
Mhm.
to those just like not that informative data? Like, what's your thoughts?
Yes, like there are like just like there are many computational methods. They are assuming like particle shape, that kind of certain like spheroid, ellipsoidal, and they are assuming the refractive index of the particles. But that may not the exact representative of atmospherically available particles. So what I stress here, my understanding is that when you have collected or measures in field or even a lab without doing proper analysis on the optical properties that is measured from the light scattering setup and concurrently your microphysical properties. First, you need to find the exact microphysical properties of the particles and corresponding optical properties. So there is the vast differences. People are assuming the particles certain safe and do the calculations and then they predict the particles. That is not exactly the truth. There is a lot of discrepancies. So my thought is that you need to have a first you need to do optical wide angle light scattering and analyze the data, and at the same time characterize the particles microphysical properties by different techniques, SEM, TEM, or other techniques. If you correlate between these two measurement, and then you can predict the uh, your results. There is a lot of uncertainty.
I see.
So
So,
again,
mhm,
people are wide angles, wide angles. Here's my thought is that they are measuring like from 10 degree or 5 degree to 170, and they are calling this wide angle. But like for lights as a light scatter, when you have like 10 micron particles, most of the light, around 50% of light falls on the first 1 degree or 2 degree, drop down.
mm,
So you are missing 50% of light when you go to the 10%, 10 degree to 150 or 160 degree. So again, I stress that when you are trying to interpret the optical properties, the experimental optical properties, then you need to have a forward scattering data as well. That will indicate the scattering in for particle size.
I see. Well, that might be this is definitely useful suggestion. Uh, but sometimes it is hard to like have all these like kind of comprehensive data for field campaigns, like when
Mm.
yeah, so that's somewhat
Yeah,
challenging.
I have
Yeah.
never been involved in such kind of field campaign data. I still don't know much what is how they are collected and
Mm,
how they interpret the data. So until now, I am solely focused on my laboratory data. So
mhm,
even based on the laboratory data, how sensitive that I show you, a small change in like 2%, 2.5% change in size distribution brings a lot change in the backscattering. So
mm,
that's how I observed in the lab. But when you go to the field, there might be many factors that is contributing to the uncertainty, not only
yeah,
particles and other particle size distribution. So I thought there is a lot of things that needs to be done. Still, there remains a lot of things
yeah,
to
true.
collect the data.
Yeah, and that definitely the finding just opens the doors to a lot of uncertainties, but also interesting things to explore.
Yeah.
Yeah. So any other questions from the audience? If if not, that probably means Prakash's presentation like is very like detailed and explains many things. So people just either understand most of them or they still need to think more about it.
Can I say one thing, like just very funny things? When I go to the triple air conference,
Mhm.
very few people come. A couple of people come to see my posters. So nobody's, I don't think like triple air is appropriate for me, but I'm trying to give triple air community from my light scattering prospectus. Here is the thing that you need to take care of, something like that. So as less interaction. When I go to the TPR conference, I found less interactions, and people are not much interested on this laboratory data. That's my thought. Maybe I may be wrong.
I think that might be something because it's very novel. That it has high novelty and very new, so people are still learning in the process. And yeah, so maybe
So
they don't
Prakash, I
know
just
as much as you do.
so Prakash, I just want to add that, this whole Q space analysis way of looking at light scattering, Chris Sorensen has been here in our center for he has been here quite a few times, including his sabbatical and also earlier, I think, last fall too. So a lot of the students here are familiar with these concepts, maybe not to the detail you have explained. Chris has also been very kind to distribute copies of his textbook, so this is really a good primer for all of us. So clearly you have a very niche and unique gap as well as a position in the AAAR community. So I just want to reinforce that.
Thank you so much. Yeah, that's where I'm looking forward. Taking the footsteps of Chris Sorensen and maybe next Chris Sorensen.
I don't know if Chris is here. Is Chris
Yeah.
here?
I think Chris is
Oh,
here.
he's listening in. Can you hear me?
Yeah. Oh, hi,
Yeah.
Chris. Yeah.
Thank you for that. That's very kind of you. I go to St. Louis every time I'm promised a dinner. So
You're always welcome, Chris. You
yeah,
know that.
thank you very much. I always like to come. You know that.
Yeah.
By the way, I have comments we can talk about with regard to your aluminum particles too. So maybe the three of
Sure.
us, we would include Hans, the four of us could talk about those problems. I think we can come up with things.
Great. Great. Yeah. Look forward to it.
I
Thank
should
you.
add, Prakash has also had another student who graduated before him, Justin Mom, who did a lot of the theory. So Justin is very active still, interacting with Prakash, Hans, and me. And so we have a nice little light scattering group going on. And Prakash, and of course, we're all very proud that Prakash managed to get a real job. So that's a major step.
Yeah. Thanks, Dr. Sorensen's comments. And if there isn't any further questions, considering that our time is about time to the end of this presentation, let's thank Professor Prakash Gautam again for his great presentation.
Thank you
Well done, Prakash.
so much.
Yeah. And Xiao Hong, thank you too for hosting.
Yeah, well done.
Well done. Yeah.
Thanks.
Yeah.
That's my job as the president of this student chapter. I'm happy to
Okay.
contribute further
Yeah.
afterwards.
Yeah.
Yeah.
Thank you.
So wish everyone a great rest of your day, and thank you all so much for joining this presentation today.
Yeah. Thank you. Bye-bye.